So yeah, welcome to the ILLIXR Consortium open meetings, and thank you for coming here and presenting your work. So for those of you who don't know Moses already, he is part of the Monado group, a part of Collabora. And if you've been on the Monado Discord at all, you know how active he is there. He's been working on hand tracking lately, and he's super excited about it, and we are excited to see the work he's done. I met him just last week and saw his talk, and it sounded fantastic. So we're looking forward to that. And he's also kindly helped to help us integrate the hand tracking that he's been working on into ILLIXR. So we thank you, Moses, and really looking forward to this. So take it away. And then I know you were asking me yesterday who are the attendees. So we have people from various places. I requested people to put their institutions next to their names if they can. Yeah, so take it away.
One second, how do I share my?
Okay, so do you see a share screen green button at the bottom of your screen?
Yeah, I do. Okay, it's working now. It was giving me like you're not allowed to. Okay.
Okay, all right, great.
Select under screen. All right, is it? Do you see my? Yes,
yep,
I think
perfect.
You do. Okay,
yeah,
cool.
Yeah.
All right. Hello. Thank you for being patient with me for the audio setup. That was annoying. I am. Actually, I already got introduced, so I'll skip past introducing myself. Let's see. So first, I'm gonna talk about like what optical hand tracking is and why we care about it so much. So basically, for a long time, we've had like 6-stop controllers.
Moses, your audio is frozen.
And these are pretty, okay. They get tracked very quickly. Really?
Well, we can hear you now. Okay. I don't know if it was just on mine. Keep talking. Okay.
Okay. It was on my Ethernet's end. So I'm on Wi-Fi now, but that's okay. So, all right. So 6-stop controllers are good for like games and art, but we want VR to be more general purpose. Like we want it to get out of your way and let you do stuff. Is my audio working now? Is it good now?
Yeah, okay. It's great. It's great.
Yep. Okay. So the main problems with controllers are you can't use them at the same time as a keyboard. So if you want to write code or talk to people online, it's very annoying.
Okay, Moses, you're freezing. Is this just me or is
and tracking your hands?
Just one sec, Moses. Is he cutting in and out for everyone else also?
Yes.
Yeah.
Yep. Yes.
Okay, Moses. I don't know what we can do. You're cutting in and out and freezing in between. So, is there something you can do quickly?
Yes. Let me look at my Okay. We shall see if that fixed it. I'm pretty sure my Ethernet cable was loose at the router. So is it working now? Does it sound good now?
Yeah.
Okay. All right. Okay, so instead of using controllers, we're just using cameras that track your hands. So this is better in a lot of ways because it means you can interact with real objects without any trouble. You can't forget your hands anywhere. You always have them. And optical hand tracking can be a lot more robust than hard algorithms that are like tracking constellations on your controllers. So, and then the really big thing is that if we could have like one input schema for all of XR that always works and that's easy to emulate in different ways, that would be really good. And it feels like just your hands could be it. And then this has already been proven out. Like a bunch of people have already done this, and it works. And we're just looking for something more open that you can base your research on without having a bunch of issues. So that's basically what I'm working on. So I'm gonna go into like some prior art that I've looked into before. So probably everybody who knows hand tracking knows about Ultraleap. Ultraleap is very good. The tracking itself is very good, but it's closed source and has a bunch of restrictions for how you can use it. And you need an extra sensor that's specialized that you can't consolidate into anything else. So it's probably not good for research for that reason. And then there's Facebook's Megatrack, which is what typically runs on Oculus Quest 2. They published a paper about this, I think 1 or 2 years ago. It's very good, and our tracking replicates some of it and takes a bunch of hints from it for other parts. But again, there's no published implementation. The data set is private, so you can't base research directly off of that. And then there's GANHands, which is similar issues. Very interesting research, but again, I can't use it. And then MediaPipe is very popular, but its data set is private, and it there's a lot of anecdotal evidence that it doesn't work very well for egocentric tracking. Like it only works well for cameras that are like not attached to your head. So I really want somebody else to look further into GANHands. It does look really good, but I don't work at a research institution, so they won't give it to me. So then the data sets are almost as important as the actual tracking pipeline. So here's a bunch of them.
What about you had MediaPipe in the previous one, so did you want to say something about that?
I did. I basically.
Sorry, did you say it? I'm sorry if I missed that.
Yeah, I basically think it's pretty good, but there's a lot of evidence that it only seems to work well for cameras that are not attached to your head, and doesn't work well on like really ambiguous hand poses. That's my opinion. You can disagree with me. I don't have hard proof. And so then data sets. You need trained data sets to train your neural nets to track your hands. So there are a lot of these. Most of them are very usable. We're using a lot of these, and like most of these are good, and like hats off to the researchers who produce them, but they have a lot of problems. Typically the problems are that they don't have sequential annotations. They don't come with camera calibrations. They don't come with 3D landmarks, and sometimes you get crazy errors or mistakes in the annotations. And then down here are some various artificial data sets. All of them have licensing issues and don't give you an easy way to regenerate your data set if you find a problem with it. So I think there's a lot more research that could be done in here, but we're kind of doing our own thing. So for us, it's like, okay, there's some good open source stuff, but licensing is annoying, and none of them feel like exactly what you want for XR. There's no really good artificial data set. And because of these problems, there's just a bunch of stuff people haven't tried out in the open yet, because there's no openly licensed foundational research that people aren't scared of using because of licensing or other stuff. So basically for us, or for me, I want to publish a bunch of resources that let you either run a finished working hand tracking pipeline that just gets out of your way, or take what we have and have it be licensed, like basically MIT or CCBY or something, and you can just do whatever you want with it. We won't bother if you don't want us to. So basically, putting it in a different way, we've already published the software. It already tracks your hands. It needs improvements, and then we need to publish all of our data sets. We haven't done that yet. We need to publish our synthetic data set. We haven't done that yet. And then we need to keep working on this and keep doing research. So now I'm going to give a quick live demo of what we're actually, like how it actually works right now, just so I can, so that I can like give you visualizations for how it actually, like, what is this thing actually doing? There's one good way to show you guys. So give me 1 second to switch my, second, yes. Okay, OBS is mad at me. Yes, there we go. Okay, perfect. So, tell me, can you see my like a through the lens view? And this okay. Actually, let me stop my screen share so that gets out of the way. Okay, so basically, oh, I think I hit the exit button or something. What happened? There we go. So this is our hand tracking as it is right now. It generally works pretty well. I can pinch stuff, move it around. I can draw lines if it'll let me. You can see this is fully 3D. I can look around and inspect stuff. You can see right here that either my handwriting is bad or the depth prediction needs work. It's probably both. But overall, this already works pretty well and gets out of your way and just tracks at high frame rate. So that is pretty good. Do I want to show you that right now? No. I'm gonna end the live demo. 1 more second. I switch back. Use the camera. And then yes, there we go. Cool. So all right, yeah. So I like to do the live demo first, because one, if there's problems, I can fix them while I'm talking, and two, it shows what I'm actually like, what the actual end goal is, so I can explain what our tracking is doing. So skip that. So this tracking pipeline has gotten pretty complicated. This diagram is pretty low level, but it's too detailed for this. But the main things I want to point out are there's three main things we're doing. One, we are looking within the camera images that we get off the headset to look for hands and also estimate which hand we think it is. And then from that, we get a region of interest that lets us estimate the pose of that hand and not bother looking at the rest of the image because we already know where it is. And then we have a real-time nonlinear optimizer, which takes the 2D hand pose estimations and figures out a good 3D pose that matches them. So that's basically what's going on. There's basically three main parts and a bunch of other stuff you have to deal with to stick them together. So
are you going to go over this in a little bit more detail later?
yes.
Because I think
Yes.
people here are interested in details. Yeah.
Yeah, I mean, the most important parts are showing you how these three components work. And then this stuff is mostly just data flow and like a bunch of annoying like decision trees. So it's mostly these three parts that you have to understand. Everything else is just a lot of code sticking them together. But yes, I'll go into more detail. So the hand detector that actually looks for your hand is pretty simple. It's pretty much just a vanilla object detector. It's got a little bit of a weird model architecture because instead of wait, what? What is being weird? Okay, instead of predicting, instead of like how YOLO models do it, instead of predicting a bunch of bounding boxes with anchors, since we already know we're only going to have two bounding boxes, we simplify it to just two heat maps, one for the left hand, one for the right hand, and then two weird heat maps that predict what we think the hand size would be for a hand centered at that pixel. And this is weird, but it removes a lot of local minima in the training, and it makes it converge towards a solution a lot faster. Like you can train one of these on CPU in like a day or so. So man, my slide controller is not working very well. Come on, go back. There we go. So the data sets we're actually using for this are mostly, oh, I forgot to put that in the prior art. Okay, I should have done that. Mostly Epic Kitchens, which is just an enormous data set, like 100 hours of people doing like egocentric video of people doing stuff in their kitchen. And it happens to have good bounding boxes that annotate left and right hand throughout most of it. There's some mistakes in there, but it's just so big that it doesn't matter anymore.
And then we also included Eagle Hands and a little bit of TV Hand and Cuckoo Hand. These two are just to increase the diversity a little bit. And then we fine-tuned on a data set we collected on My North Star to mostly because all of these data sets don't have a whole lot of fisheye video, and they also don't have a whole lot of people doing really weird things with their hands. It's mostly just people grabbing stuff. So we're training in PyTorch, and the hand detector is not published yet because the code is very, very, very messy, but it will be published soon. And then, so it's we have kind of a cool annotator. Basically, we trained a neural net that tries to detect your hands, and wrote a program that just takes you to that, like, one lets you confirm that the annotations are correct, and two lets you add or fix them. And it lets you do this through sequential video, so you only have to annotate once every few frames. So that made things pretty simple, and I think we got like about 10, 12,000 well annotated frames, and that felt like enough. And then when we're is my video still working well? Just checking. Okay, is my video still working well?
I don't see anything playing right now. It was okay before, although it was not particularly smooth. Are you playing something right now?
I am not. It is, but you can see my presentation slides though, right?
Yeah.
Okay, I was just making sure that Zoom's UI changed, and that made me nervous. Okay. So for training, we're doing very simple data augmentations. We're just adding a small random rotation and scaling to the input image, and just obviously rotating and scaling the annotations with them. This is all you really need. You don't, for egocentric hand detection, you don't need to do very crazy data augmentation, because you actually want it to, you want it to overfit a little bit to the constraints of egocentric video, like basically that you can see somebody's arms foreshortened out of the video frame, and in general they just go back towards the user. So that's good. Pretty simple training pipeline. And then you can see here's a very simple view of it running in real time. I think here you can see it doesn't care if I cross my arms over. It's oh no, I break it at the end, but it usually doesn't care. It usually gets the hand in this right. It works well enough. Google Slides really doesn't like me. Okay, there we go. And then the keyboard estimator is exactly the same as Megatrack. Like even the model architecture is the same. It just does the same thing. The one thing we changed is that in Megatrack, the input is 96 by 96, but since we're running on desktop and we have much more memory and much higher memory bandwidth, we bumped it up to 128 by 128. That seems to make it slightly less jittery, but overall, we don't have a conclusion there about how big any of the model inputs should be. This is something we need a lot more research into, and we need to train like models that see in RGB and models that see using depth cameras. There's a bunch of stuff to do here, but overall, this works pretty well. This is this is mostly using the CMU panoptic dataset and freihand, and then a really small dataset I collected, and then the artificial dataset that is like that's like the foundation of how we're doing this. So again, just very quickly, this is what our key point estimator sees. It just sees a very cropped image of your hand, and then it outputs heat maps that describe the probability distribution of where it thinks each hand joint is. So like you can see this corresponds to your index fingertip, and you can see it lines up an image, and like that's your wrist, and that's your pinky fingertip. So probability distributions, that's an important one, because there is a lot of uncertainty in egocentric hand tracking sometimes. So this is actually giving us Gaussian distributions that we can estimate, for which we can estimate the center and variance actually correctly, makes things a lot easier. And then also it gives us just one-dimensional Gaussian, well, they try to be Gaussian distributions. You can see a lot of these are pretty binodal sometimes if it gets confused. But again, these are trying to predict each joint's depth relative to the middle proximal joint. So that all works pretty well. There's a lot more experimentation to do, but overall, I'm pretty happy with it. So just as a review, there's a lot of problems with public hand landmark data sets. Basically, sorry, give me 1 second. Okay, basically most of them don't have sequential annotations. A lot of them don't have good 3D annotations with depth. Very few of them have camera calibrations, and almost all of them have incorrect annotations. And everything has licensing issues, and everything has privacy issues. Like you can accidentally get somebody's fingerprints in there. You might not want to collect in somebody's house. And then if you're collecting one of these, it's kind of risky because you always have the chance of losing data or spending too much time annotating your data and you run out of time or money. And getting the right kind of cameras are expensive. So basically, instead of doing that, I was wondering if there's like a smart way around all of these real world problems, and turns out that there is. So this is just like a collage of random pictures I generated. Like none of these are real people's hands. These are all hand scans that we animated and rendered and then distorted to look like fisheye cameras. And this solves a lot of problems because it means if we don't like something in our data set, we can just regenerate it in a few hours and hopefully solve that problem. So, no, I don't want. Oh my gosh, Google Slides really hates me. So again, like we looked a lot into like using generative models to just generate hand meshes that magically look correct. It's really interesting to watch diffusion models basically catching up and outpacing GANs, but so far there's still nothing ultra realistic yet. So we're just using hand scans using photogrammetry from an asset store. So these aren't published yet, but they will be soon. And basically, we just rig them in Blender, and we have a fake mocap data generator that basically just stochastically generates a bunch of hand poses. And then we have a very crazy data generation pipeline that's like it's like a C++ program that launches Blender a bunch of times and generates a bunch of these data sets at once. This works pretty well. I'm pretty happy with it. It still needs a bunch of work though. So then training the Kubernetes estimator, very similar to the hand detector. Also just PyTorch and sticking a bunch of data sets together. One thing I want to shout out is Nunchucks. It's a very good Python library for if you find mistakes in a data set that you didn't catch before you're already training, you can just tell your data loader, oh, this one isn't bad, you don't use this one, and it won't. As opposed to vanilla PyTorch, which just crashes the whole program. So that's very useful. And then we have a fancy loss function that basically ignores different parts of our loss function. Is basically just L2 loss, but we have to have a bunch of fancy stuff in there to ignore, for example, the depth prediction since a lot of our samples don't actually come with depth. We can just not run the loss on that and not get gradients propagating back from there. So that works pretty well, and we actually keep using this pattern of just ignoring parts of the loss when they're not useful. And then the training code is already published, and I'm getting pretty happy with that. I think it'll start being generally useful very soon. So, and then the last bit, which is not a neural net, is it's just a classical algorithm. Is basically you have the problem of you have a bunch of predictions in camera space about the hand's pose, but you want to extrapolate them into 3 dimensions. This is like fundamentally an annoying problem because like you can use triangulation to try to get a rough depth value, but if any of your predictions from the neural nets are wrong, this depth is going to be super wrong. It's also annoying to try to assign a variance to just triangulation. And it's also very annoying to actually try to fit a hand skeleton to any 3D positions, because the skeleton needs to actually be correct. It needs to like not bend backwards. It needs to not have its joints become super long if your model predictions are wrong. So basically, instead of trying to use inverse kinematics or trying to use a bunch of like by hand math, instead we can basically just use gradient descent to basically assign an objective function to how far away the like sorry, I keep explaining things wrong. So basically, instead of writing a bunch of code by hand, you take a low-dimensional vector encoding the hand pose, which includes stuff like the hand size and the wrist pose with its position and orientation relative to the camera, and then a bunch of curl values for different ways your joints can bend. You write a function that takes this vector, I think it's like 27-ish values, evaluates all of this to a 3D hand pose, and then projects the positions back into camera space. And then the metric is basically just how close are these poses to the model prediction. And then you can just, and then there's this algorithm we like called Levenberg-Marquardt that basically can query this function that we write by hand, and ask it how close this hand pose is and how close this hand pose is. And then after about 50 iterations, it comes up with a good solution on its own, and we don't really have to mess with that. It just works really fast. And this technique keeps getting used like over and over in a lot of VR tracking. Like we use it for head tracking and controller tracking, basically for the same purpose, but instead of optimizing a bunch of curl values, it's usually just optimizing the 6-off pose of your hand. So this is good. We like this. It's really flexible. You can just add stuff to your objective function, and it will come up with the optimal solution according to what you asked for. And it doesn't really care if your system is under constraint. Like if you're operating with an egocentric with a monocular camera, like just one camera looking at your hand, you're basically always under constraint because you're let's see. Because you have just one set of 2D predictions, and you're trying to extrapolate them to 6-off poses. Like you have way more inputs than outputs. No, way more outputs than inputs. So that's under constrained. And that still works. And exactly constrained systems are fine. And over constrained systems, which is what hand tracking usually is for stereo views, that also works fine. So this is a very good solution. We looked into Kalman filtering to do this, and it was going to look like we had to do like at least iterated Kalman filters, which was going to be annoying and expensive. So nonlinear optimization is usually just better. And then to actually do this, we're using a really small fork of series, which just has like this one part we like. So series is really good. I highly recommend it for if you're researching your own tracking task. If you want to do it in real time, you probably need series to do some optimization thing for you. So, and then again, here's like, basically, here's a bunch of examples of what random tasks you can ask nonlinear optimization to do. So okay, this one might not show up super well on video, but basically what this is doing is I'm basically generating a random kinematic chain, and it's estimating each joint's rotation value just on the basis of how far away is our model pose from the measured pose, and it basically estimates that very quickly. I'm not going to unmaximize, is it? There we go. So that works. You can also see that like we can also use it for point cloud alignment. Like here, it's going to align these 2 point clouds in like 6 iterations. Again, just on the basis of on the basis of like just one distance metric of how far the model is away from the measurement. And then here's like trying to make it full screen. There we go. And then here's what we actually made it for. Is basically you have a bunch of 2D predictions, and the nonlinear optimizer's job is to extrapolate them into 3D. You can see that when I was working on this, the data set I had collected had like a big mistake in the model outputs, and it did freak out here. But overall, this just works very well. So let's see. Trying to go to my next slide. It doesn't want me to. Go to the next slide. There we go. Okay. When I embed YouTube videos in my slides, when I try to go to the next slide, it instead plays the video. It's very annoying. But so that's most of presenting what we've already done. There's not that much more detail to go into without like actually looking at the code. Overall, a lot of this is simple concepts, complicated execution, and also a lot of code that was previously unpublished, and a lot of models that were, and a lot of papers that like previously didn't show you how they did everything. But for us, the code is published, so you can just look at it if you want. So basically, for us, the like near term goals we have to make our tracking better are, most of them are just improving our artificial data set, because most of the big problems with our tracking are just that our data sets don't always represent everything that egocentric cameras actually see. So a lot of this is just like we need to include a bunch of long sleeves in our training data. We need the artificial data sets to look a little bit more anatomically correct. Like a lot of the time, the poses it generates look really silly. And then I really want to take like some fast looks into soft body simulation of the skin instead of just using normal armature linear blend skinning. We need to generate more data and do stuff like intertwining fingers and intertwining hands, and then also be able to simulate depth cameras and event cameras. So that's the main goals for our data set, which will be happening this year, basically. And then another big thing is we want to look at like how accurate can you make egocentric optical hand tracking. Like there's always some ambiguity in the tracking because you can't see all of somebody's hand from just their headset. So we want to try training very slow but very accurate models and see where, if anywhere, they still make mistakes. One thing I really want to try here is basically making a diffusion model that instead of generating an image using a text prompt. It generates a prediction through diffusion using the input image as a prompt. I haven't seen that tried before. I'd really love it if somebody, if anybody knows anything about that, because I don't think that's been tried yet. So there's that, and then we want to try a bunch of stuff in the nonlinear optimizer. Like I can see it making mistakes sometimes, and we need to fix those. And then there's a bunch of relatively small things I want to try in our real-time models. Like one thing I really want to try is a key point estimator that where instead of feeding it just one image, you feed it both in views of a stereo image, and so that it gets as much context as possible. And then I want to try a refinement model that can fix up the region of interest in case your hand moves really fast and the predicted region of interest is wrong. So there's a bunch of stuff to try, and we just need to try it. And then we also need to do elbow tracking and non-egocentric tracking, and we need to publish it. So, and then again, because there's a bunch of researchers here. Here's a bunch of crazier stuff I want people to try, and that I think our tracking might be a good jumping off point for. A lot of these are crazy and would represent a long time working on it. A big one is I want to make a modular nonlinear optimizer that basically takes SLAM tracking data and hand tracking data and anything else and optimizes it all into a full upper body pose for you, so that basically you can get the advantage of the full context of what a headset is seeing, and this would let you save a lot of compute in certain places. And then a big thing we should probably have is better pose prediction. Sorry. Like basically better pose prediction, probably using neural nets. That probably would do a lot better than basically just straight line pose prediction. And then a really fun one is I really want to try a reinforcement learning agent that tries to beat Levenberg-Marquardt in optimizing basically narrow systems. And this one, the main point of it is like not a general agent, but something that that understands the global manifold of like hand tracking or body tracking and can iterate towards a good solution a lot faster. And then the last one is event cameras. Basically, event cameras, instead of giving you distinct individual frames, for each pixel, they just asynchronously report any change in brightness. And that can happen at like a few thousand hertz instead of like a few tens of hertz. So event cameras are still expensive, and they are still not used in VR headsets, but I'm pretty sure in the next 10 years, they're going to get used a lot more because they're just much better for fast tracking. There have been a few papers published about event cameras, which I'm happy about. So, okay, that is, let's see. That is pretty much the end of my presentation. Basically, we are, how can I summarize? We are just doing optical hand tracking. Basically, we're trying to publish a good base for people to do other research on, and we're getting pretty close. So we are hiring. Like at Collabor, we do a bunch of stuff. We don't just do XR. And we do a lot of open source software. And the cool thing is that basically you get to own what you're doing, and you get to use your work without it being hidden behind a bunch of NDAs. So if anything we're doing looks interesting to you, like please contact one of us and see if working at Collabor might be good for you. So that is the end of my presentation. I am very dehydrated. Is it okay if I run and get a glass of water and come back for questions?
Yeah,
Okay.
sure. Yeah, we don't have
Okay.
much time, but yeah, that's
Yeah.
fine.
Give me like 1 minute. I'm like, I
Perfect.
need water.
Yeah,
Okay.
yeah, of course.
Thank you.
So Kevin, you have been working with the Monado code. Do you have any specific questions for Moses?
Okay, so I guess like right now I think like I have a lot of my questions answered because I asked them this morning on Discord.
Okay, cool.
But
All
yeah.
right, great. Okay.
Okay.
Hi. Great.
Hi.
So let's see. Does anyone have a question? As I have a few.
Can I have a question first?
Yeah, please.
So in your demo video, I don't think you demonstrated how good your hand tracking performs when, for example, like one finger is on the other one from the camera, like from the camera's perspective. So how well is that with your hand tracking algorithm?
Like, do you mean like intertwining fingers or overlapping hands? Or
overlapping hand is one point, and another point is, for example, if you have a look at my camera now, so for example, if I have my middle finger is like, I mean, my index finger is behind my middle finger, things like that. So how well is that on your tracking?
Oh, like basically just your hand being
Hands pointing
flat over
up, or
okay.
exactly.
Okay, so let me switch cameras again. Okay, so basically it usually does pretty well with your hand being exactly flat. You can see the jitter increases kind of noticeably. That it happens. I would say a big part of this is our data set isn't good enough. And then intertwining fingers do not work yet. Like it doesn't know what's going on here. You can see it's kind of just lerping in between. So that doesn't work. And then overlapping hands are often fine. But it's hard coded to stop tracking them if they overlap too much.
Okay. Because I think
Does
this
that answer your
question
question?
has been, I mean, thank you very much. And I think this has been like investigated by the Interhand 2.6M dataset, right?
Yeah.
I think they have some, okay, thank you. So another question I have is, for example, in all your demonstrations, I think the hands are like pure hands, so without any, for example, like I have a ring on my middle finger. So will that affect your tracking or something?
So small things like rings shouldn't affect it at all. And in general, it's just a matter of making sure that the training data sets include some rings and still have correct annotations. So our data set probably doesn't have enough stuff like rings and watches, but since it's an artificial data set, it's very easy to add in, and it will be added in.
Okay. So, like, for example, rings, watches, or even gloves. Okay, thank you.
Yeah, but definitely medical gloves. Bigger gloves might get harder, but definitely
Okay.
small gloves. Yeah.
Yeah, makes sense. Thank you.
Others have questions? We are out of time, but we can take a couple more minutes, I think.
Yeah, I have nothing going on. Totally
Okay,
fine.
yeah. I think some of us need to leave. And then just for the others who are attending, our next speaker, which will be 2 weeks from today, is going to be Professor Neil from UC Riverside, and he will be talking about security issues with heterogeneous accelerators and so on. So that should be very interesting, and we'll send an abstract soon. Okay, so Moses, I had a question related to, so thanks for the great talk and for coming here. So is this integrated into Monado, or is this a standalone component right now?
So it is obvious. As you might expect, the training pipelines and the dataset stuff are totally separate.
Yeah, I mean the inference.
Okay.
Yeah.
The inference stuff is a part of Monado, but it has a C API and you can build it separately. And it's designed to not use that much of Monado's core. So if you want to submodule Monado and give it other inputs, that should be very easy. And if you run into problems, I want to know about them because that is a use case that we want to support.
Yeah, sure. Thanks. And then what is the performance of it, right? So where are you running this, and how long does it take, etc. So clearly it's working in real time, but I'm trying to understand from a headset's performance and power point of view, where do we stand?
So right now it's
again, I'm only talking about the inference part, right? Just the real time part.
Yeah. So right now it's not optimized, and it is running on 2 to 4 threads on my CPU. I think it's about 50-ish% occupancy, and I'm mostly using all those threads to lower latency. So I believe it's on the order of 2 milliseconds for the key point estimator, and maybe like 5 or 6 for the hand detector right now. The hand detector is very slow, and we need to replace it because it's just not an efficient model. And then the nonlinear optimizer takes about half a millisecond, and that's also unoptimized code. I pretty like it was pretty much once it worked fast enough, I stopped optimizing it. So there's surely a bunch of overhead in there you could get rid of. And then another thing that's easy to point to is that since this is based on like Megatrack, like Facebook's paper for Oculus Quest 2, you can see that they got their key point estimator and hand detector running in real time on like this tiny DSP. So overall, it's small models running fast, and there's a bunch of room for optimization. And since it's all using Onyx models, it should be pretty easy to port to other inference platforms. Like if you have like some embedded system, usually if it has a TPU, they have an inference platform that lets you shove an Onyx model in there, and that should be easy to port. But
so where are you running this? So you said CPU. So are you running it on a CPU or a GPU or
CPU?
It's on a CPU.
Yeah. In general, on desktops, we like to run neural nets on CPU because we want to leave the GPU alone so it can render stuff. But it would be awesome if people would just have tensor processing units like dedicated in their machines. But in general, CPU is fine and works well enough.
Okay. All right, great. So you listed a lot of things that you want to improve on. Like, what is sort of, what are some of the burning issues that you feel kind of restrict the XR experience today with this hand tracking? Or do you think it's pretty good already?
Like, so the overarching problems that still need to be fixed are the data set. But there's also probably a lot of quality of life issues where the hand detector will mistakenly think something is your hand, and it'll like track a hand over there, and it might this ghost hand will like press a button or something. That's probably the most annoying one right now. And it's mostly a matter of tuning our rejection stuff to decide more accurately, oh, this isn't a hand. So but it's mostly like really small quality of life issues that you can work out in like a day or so. And the rest of it is improving the data set and then basically just a bunch of trial and error, like trying slightly different model architectures. That's what I'd say. Does that answer your question?
Yeah, I was looking for more like in terms of the experience itself, right? What do you see as like the major kind of, I wish I had this feature kind of thing as the end user?
It's the end user. I still don't quite understand your question because it's like,
okay, so an example is, so the overlapping hands you said, right? It's not that good at it, but you might argue that, okay, that's something we can live with maybe, right? So in that vein, I'm trying to figure out like where are the sources of inaccuracy that really bother you?
Okay. Okay, that makes more sense. Yeah, the thing that really bugs me is that there's still a small amount of jitter, and it's somewhat unclear why. I'm very sure we're gonna figure it out, but it's there. But yeah, it's just a bunch of small stuff, and it's probably a big part of it is just improving our data set and improving the model architectures. But yeah, it's like jitter, quality of life, and we do want to track overlapping hands, but it's not all that important. Yeah.
Yeah. Okay. Thanks. Other questions from others here?
Hi, I have a quick question. My name is Armand from the University of Michigan. I'm a big fan. And yeah, I was just wondering for AR, do you think there's always going to be like a digital hand overlay? Do you think that's something users are going to need?
I think probably not.
Okay.
A lot of people do it because it's cool. Like StereoKit does it basically to say like, look, your hands are being tracked. The computer's doing something. And obviously I'm doing it to basically for the same purpose. But yeah, HoloLens is a good example of their system UI does not display your hands at all. It does have like it does its hand tracking does cause like occlusions over the system UI. So like if you put your hand over some virtual object, like it'll look like your hand's covering it up, but besides that it doesn't do any overlays. And that's where I think we're going. It's mostly just for me like debugging stuff, showing people what it's doing. I need it. And also with my my North Star build, the alignment between the sensor and the displays isn't exactly right. So sometimes I have to watch the overlay more than my real hand. In some cases, usually not, but sometimes.
I understand. Thank you.
Okay, great. Last call for questions. All right. Thank you so much, Moses. Really appreciate it. And we'll be in touch, I'm pretty sure.
Mhm.
Yeah, thanks. And thanks everyone for joining.